Section 1.3 Vector Equations. A matrix with only one column is called a column vector, or simply a vector. For example, this one has 2 components and this one has 3 components. So it is a vector in R2. It is a vector in R3. In the first part of section, we'll consider vectors in Rn. We'll begin with vectors in R2 for simplicity. We can identify a point AB with a column vector. In this case, we call it a position vector. In the left figure, we have 3 points. We may consider a vector starting from the origin to the point, as in the right figure. Then, for example, this vector is the position vector for this point. And for the other points, you can define the corresponding position vector. Vectors are mathematical objects having direction and length. We may try to compare them, add or subtract them, multiply them by a scalar, and measure their length, and apply other operations to get information about angles. You learned various mathematical objects from elementary school and high school. For example, you begin with natural numbers, and 1, 2, 3, 4, and so on. And by adding, you got whole numbers, and considering the adding negation of natural numbers, you had integers. And now integer over integer, the collection of those numbers become rational numbers, and later on, by adding irrational numbers, you got real numbers, and finally, you considered the complex numbers. These are all mathematical objects, and you applied the 4 basic operations: addition, subtraction, multiplication, and division. Vectors are mathematical objects, so that we may try to apply those operations, but we have to apply meaningfully. So here, 1, 2, 3, 4, 5, we'll consider such kind of operations. Anyway, here, vectors are mathematical objects having direction and length. Okay? Equality of vectors. 2 vectors, u and v, are equal if and only if corresponding entries are equal. That means that here, first entry must be equal, and second entry is also equal. u2 v equal v2, u1 equals v1. Then we say 2 vectors are equal. For vector addition, we define in this way: uv, u plus v, and that is u plus v, and component-wisely we add the entries. That is definition of a vector addition. Here, scalar multiple or scalar multiplication. The c is a scalar, which means a real number. Then we can multiply the vector v by a scalar c. Then c will be multiplied for each component. That is definition of scalar multiplication. Okay. Quite naturally, we define it this way. Parallelogram rule for addition. if u and v are represented as points in the plane, then u plus v correspond to the fourth vertex of the parallelogram, whose other vertices are 0, u, and v. Look at the figure. If u is given in this way, and v, and its addition is the fourth vertex of this parallelogram made by here u and v. You can figure out this one quite easily. And u plus v means that first you move along u, and from here now v. So v is that one, so that along with that parallelly here we make that one v here now. This portion is v. So u plus v makes here terminal point u plus v. If we consider these vectors as, we try to identify these vectors as the position, then here u is this one, and u plus v will be this position. Okay? Okay. Here, u and v are given here, and find u plus 2v and 3u minus 2v. Okay, let's begin with u plus 2v. Okay, that is u is now here 2 and 1, and here twice of v, 1 and minus 3. Okay, then there is 2 and 1, the u vector, and scalar multiple makes here now 2 and minus 6. Okay, now by using the vector addition, that will be 4, and component wisely we are adding these entries. 1 minus 6 is minus 5. Okay, for the other one you can do it similarly. Okay, let's try to display u plus 2v. Okay, here we have now, okay, u is 2 and 1, x is to second component is 1, so that we have that one, that is u. Okay, that's u from here to there. Okay, v is x is 1, y is minus 3, so that 1, and here 2, 3, minus 3, so that we have that one. So that is now a v. Okay, that is v. Now u plus 2v means that first we move along the u here. Now parallel with this v, we are moving 1v and another v, 2v, so that eventually that one will be u plus 2v. Okay, that is here x is 4, y is minus 5. Okay. The same vectors we considered here, we rename them a1, a2. Then by using some general coefficients x1, x2, we consider x1 times a1, the scalar multiple, x2 times a2. Then we can write in this way. Then now here, okay, scalar multiple, and then vector addition, we can reach that one. Now, using the knowledge we learned from earlier sections, here, this can be written as in this form. We have the quotients 2, 1, and 1 and minus 3, and an x1, x2. So here, the first one is, the first column is a1, the second column is a2, so that we can write in this way. Here, this equation is saying that this the scalar multiple and vector addition can be written as now metric vector multiplication, and such term is called the linear combination of two vectors a1, a2. Will define that in the later part of the section. And here the main thing is this combination can be written as metric vector multiplication. Okay, we'll deal with this issue later on in detail. Now we considered so far vectors in R2, but for vectors in Rn, the above vector operations, including the parallelogram rule, are also applicable for vectors in R3 and Rn in general. So that even though we defined here vector addition and scalar multiple, and also we consider parallelogram rule for addition for two-dimensional vectors, but they can be applied for general dimensional vectors. Okay, and also the vectors have these properties. If u, v, w are in Rn, in general n, and scalars c and d, then u plus v must be same as v plus u. And if we add three vectors, then we can add the first two first or last two first. Once 0 is added, then it's not changing. For given vector u, if you add minus u, then it will become 0. And here, minus u is the same as minus 1 times u. And vector addition and scalar multiple can be done along with the same scalar multiple for each vector and vector addition. And once the scalar are added and multiplied to u, then this can be done here. One scalar, each scalar is multiplied to the vector u and added. Okay. Now for the multiple of scalars can be done at once. In practice, this one will be more efficient. This one requires d multiplication for each component of u, and later on c multiplication for each component. But for that one, you can get cd once, and the quantity will be multiplied to all components of u. If scalar 1 is multiplied to a vector, then it is not changing. Okay. Okay, that's the first part, and we'll continue in the second part. Thank you.